You're sitting in space right now, or at least that's what you think. You believe you occupy a specific location in three-dimensional space, that there's distance between you and the walls around you. That space is the stage where everything happens, the container that holds all of reality. But what if I told you that space doesn't exist? Not in the way you imagine, not as something fundamental. I've spent 50 years thinking about what space is, and the answer I've arrived at terrifies me a little. Space isn't a thing. It's not made of anything. It doesn't exist independently of the objects in it. And most disturbing of all, it's not even clear that space is real in any fundamental sense. What we call space might be an illusion, an emergent phenomenon that appears at large scales but dissolves when you look closely enough. Let me start with the obvious question. What do we mean when we say space? Most people picture an empty void, a three-dimensional grid stretching infinitely in all directions. You can put objects in this space, move them around, measure distances between them. Space is the background, the arena. It was there before objects, and it'll be there after. That picture comes from Newton. He needed absolute space for his laws of motion to make sense. An object at rest stays at rest. But at rest relative to what? Newton said relative to absolute space itself. Space provides the reference frame, the fixed background against which motion is defined. Einstein destroyed that picture. Special relativity showed that there's no absolute space, no preferred reference frame. Different observers moving at different speeds slice up space-time differently. What one observer calls simultaneous events, another observer says happened at different times. Space isn't absolute, it's observer-dependent. Then general relativity went further. It said space isn't even flat, it curves in response to matter and energy. The geometry of space changes depending on what's in it. So space can't be a fixed background. It's dynamical. It participates in physics rather than just hosting it. But even Einstein's picture assumes space is real. It's not absolute anymore, it's not fixed, but it's still there. It still exists as a geometric structure, curved or flat, dynamical or static. Space is something, and for most of the 20th century, physicists accepted that. Space is real. We're just refining our understanding of what kind of thing it is. Then quantum mechanics entered the picture and everything fell apart. Quantum mechanics says that at small scales, reality is fundamentally uncertain. You can't know position and momentum simultaneously. The more precisely you measure where something is, the less you know about where it's going. That's not a limitation of your measuring devices. It's a fundamental feature of nature. Position itself is uncertain. Now think about what that means for space. If position is uncertain, then what does it mean to say an object is located at a specific point in space? The electron isn't really at position X. It's in a superposition of many positions, a spread-out wave function. Only when you measure it does it collapse to a definite location. So is space real if positions aren't well defined? Is there a background of points even when nothing occupies those points definitively? Most physicists said yes, space exists. Quantum mechanics just makes the objects in space behave strangely, but the space itself is still there. I'm not so sure, and here's why. When you try to combine quantum mechanics with gravity, when you try to build a quantum theory of space itself, you run into fundamental problems. Space stops making sense as a concept. The problem appears when you try to measure distances at very small scales. According to quantum mechanics, measuring anything requires energy. The more precisely you want to measure, the more energy you need. Now imagine trying to measure a very small distance. The Planck length about 10 to the minus 35 meters. The energy required is enormous. And here's the issue. If you concentrate that much energy in a small region, you create a black hole. The very act of measuring the distance changes the geometry so drastically that the concept of distance becomes meaningless. You can't probe space below a certain scale because probing it destroys the thing you're trying to measure. This suggests something radical. Space might not exist at arbitrarily small scales. There might be a fundamental limit to how finely you can divide it, not because we lack technology, but because space itself becomes ill-defined. Some approaches to quantum gravity take this seriously. Loop quantum gravity says space is made of discrete chunks, tiny loops of geometry connected in a network. At large scales, this looks smooth, like how a TV screen looks smooth from far away, even though it's made of pixels. But zoom in and you see the granular structure. String theory says something different but equally strange. It says that at very small scales, the distinction between small and large breaks down. A string moving in a tiny circular dimension is mathematically identical to a string moving in a large circular dimension. The physics is the same. You can't tell which description is correct. Radius stops being a meaningful concept. Both approaches suggest that space is not fundamental. It's emergent. It appears at scales we're familiar with, but it's not part of the basic description of reality. What does emergent mean? Think about temperature. You can measure the temperature of a room, but temperature isn't a fundamental property. It's the average kinetic energy of countless molecules. The molecules don't have temperature, only the collection does. Temperature emerges from a more basic description. I think space is like that. It's a useful concept for describing collections of events or quantum states, but it's not fundamental. The fundamental description doesn't include space at all. Space emerges from something else. From what? The best answer we have comes from studying black holes and something called the holographic principle. Black holes are the key to understanding quantum gravity. They're places where space-time curvature becomes extreme and quantum effects can't be ignored. Stephen Hawking discovered that black holes have entropy. They contain information, and the amount of information is proportional to the area of the event horizon, not the volume. That's bizarre. Normally, entropy scales with volume. A bigger box holds more gas molecules and therefore more entropy. But black holes are different. Their entropy depends on surface area. Why? The holographic principle gives an answer. It says that all the information in a volume of space can be encoded on the boundary of that volume. Like a hologram encodes a three-dimensional image on a two-dimensional surface. The interior of the black hole, all the information about what fell in, is somehow encoded on the event horizon. And if that's true for black holes, it might be true generally. Maybe all of three-dimensional space is actually information encoded on a two-dimensional boundary. What we experience as depth, as the third dimension, is an illusion, a reconstruction from boundary data. This sounds insane, but there's mathematical evidence for it. The ADS-CFT correspondence discovered in the context of string theory is an explicit example. It describes a universe with gravity in terms of a quantum theory without gravity living on the boundary. The interior space, the place where gravity operates, emerges from correlations in the boundary theory. Let me say that again because it's important. There's a mathematical equivalence between a theory with space and gravity and a theory without space or gravity. They describe the same physics. One formulation has three dimensions, the other has two. Which one is real? Neither, or both. They're different descriptions of the same underlying structure. This is what I mean when I say space isn't fundamental. The fundamental description doesn't need space. Space is a way of organizing information, a useful bookkeeping device, but it's not the territory. It's a map. And like any map, it's a simplified representation that works for certain purposes but breaks down in extreme situations. What is the territory? What's the fundamental thing that space is a map of? I think it's quantum information, relationships between quantum states. When you have quantum systems that are entangled, correlated in specific ways, those correlations give rise to geometric relationships. Distance emerges from the pattern of entanglement. This idea has been tested mathematically. You can start with a collection of quantum bits with no notion of space, just abstract quantum states. Then you entangle them in particular ways. And when you do, a geometric structure emerges. Points that are highly entangled act as if they're close together in space. Points that aren't entangled act as if they're far apart. Space is the pattern of entanglement. Geometry emerges from quantum information. And when the entanglement pattern changes, space changes. It can curve, it can expand, it can even tear if the entanglement is disrupted. Does that mean space is an illusion? Not exactly. Illusions are things that seem real but aren't. Space seems real, and in a practical sense, it is real. You can measure it, build things in it, navigate through it. But it's not fundamental. It's like saying money is an illusion. Money has real effects. You can buy things with it. But at a fundamental level, it's just an agreement, a social construct. Take away the humans and money doesn't exist. Take away quantum information and space doesn't exist, at least not in any fundamental sense. What you have is a collection of quantum states with certain correlations. Space is how we describe those correlations when we look at them from a particular perspective. Now you might be thinking this is all very abstract and mathematical. Does it matter for everyday life? Does it change anything about how space works in practice? No, just like you don't need to think about atoms when you drink water. The emergent description works perfectly well for everyday purposes, but it matters for understanding the universe, for understanding what happened at the Big Bang, for understanding what's inside black holes, for understanding whether space is infinite or finite. These questions don't have simple answers if space is fundamental, but if space is emergent, they become different questions entirely. Take the Big Bang. We usually imagine the universe starting from a point and expanding. Space itself expanding, carrying galaxies with it. But if space is emergent, then what does expansion even mean? Is space really expanding, or is the pattern of quantum entanglement changing in a way that we describe as expansion? I think it's the second one. The Big Bang wasn't the creation of space. It was a transition in the structure of quantum information. Before the Big Bang, or whatever we should call that moment, information was organized differently. Maybe there was no space at all in the usual sense. Then something changed. The information reorganized, and what emerged from that reorganization was the expanding space we observe. This changes how we think about the beginning of the universe. There doesn't need to be a first moment. There doesn't need to be a singularity where everything was infinitely dense. Those concepts assume space and time are fundamental. If they're emergent, then the beginning could be something else, a phase transition, a change in the way information is structured. And what about the end? Does space go on forever? If space is fundamental, that's a meaningful question. Either it extends infinitely, or it has boundaries, or it curves back on itself. But if space is emergent, the question changes. It becomes a question about information. Is there a finite amount of information in the universe, or infinite? And how is that information organized? We don't know the answers, but the questions themselves are different, and that matters. It means we might be looking for the wrong things, asking about the wrong properties, trying to measure aspects of space that don't correspond to anything fundamental. Let me give you another example. Dark energy, the mysterious force that's causing the universe's expansion to accelerate. We measure it, we know it exists, but we don't know what it is. Some people think it's a property of space itself. The vacuum has energy. Empty space has a tension that pushes things apart. But if space is emergent, then vacuum energy is a strange concept. Empty space isn't really empty. It's full of quantum fields fluctuating. Those fluctuations have energy. But why should that energy cause expansion? Maybe the expansion is telling us something about how the underlying quantum information is reorganizing. Dark energy might not be energy at all. It might be a signature of how entanglement patterns evolve. I don't have answers. Nobody does. But I think we're asking the wrong questions because we're still thinking of space as fundamental. We're trying to understand dark energy as a substance filling space. But maybe we should be thinking about it as a feature of how information is organized. Here's another puzzle. Quantum entanglement. Two particles can be correlated in such a way that measuring one instantly affects the other, even if they're light years apart. Einstein hated this. He called it spooky action at a distance. It seems to violate the principle that nothing can travel faster than light. But here's the thing. If space is emergent from entanglement, then there's no mystery. The particles aren't really separated by space. They're connected at a deeper level. The space between them is an illusion created by looking at the entanglement pattern from a certain perspective. When you measure one particle, you're not sending a signal across space. You're revealing a correlation that was always there in the underlying quantum state. Space makes it look like the particles are far apart, but fundamentally they're not. They're part of the same quantum system. The distance is emergent, and entanglement is the more fundamental relationship from which distance emerges. This flips our usual understanding completely. We think particles are in space, and sometimes they get entangled. But actually, entanglement is primary, and space is what appears when you have certain patterns of entanglement. Particles that are highly entangled define what we mean by nearby. Particles that aren't entangled define what we mean by far apart. Now let me address the obvious objection. If space isn't fundamental, then what about all of physics? Newton's laws, Maxwell's equations, general relativity. They all assume space exists. Are they all wrong? No, they're not wrong. They're effective theories, descriptions that work at certain scales, like thermodynamics works even though we know matter is made of atoms. You don't need to know about atoms to predict how steam engines work. Similarly, you don't need to know about quantum information to predict how planets orbit stars. Space is real as an emergent phenomenon. The laws of physics that describe space are real effective laws. They work, they make predictions, they're not wrong, but they're not the deepest description. There's something underneath. And at extreme scales where quantum gravity matters, at the Planck scale or near black hole singularities, the emergent description breaks down. That's when you need the fundamental description, the one without space. And we don't have that description yet. Not completely, we have pieces. The holographic principle, ADS, CFT, loop quantum gravity, string theory, but we don't have the full picture. What would that picture look like? I imagine it's a quantum theory defined on an abstract space of states. Not physical space, Hilbert space, or something like it. The states are related by operators, by transformations, and certain patterns of states, certain correlations, give rise to what we interpret as geometry. Time would be emergent too, not a separate dimension flowing forward, but a way of organizing how states evolve, how correlations change. The arrow of time, the fact that we remember the past but not the future, would come from entropy, from the fact that information flows in a particular direction. And observers, where do we fit in? If space is emergent, then so are we. We're patterns in the quantum information, subsystems of the total state, and our perception of space comes from how we interact with other subsystems. The geometry we perceive is relative to us. Other observers might carve up the quantum state differently and perceive different geometry. This sounds like solipsism, like I'm saying reality is whatever you perceive it to be. But that's not what I mean. There's an objective quantum state, a real structure. But how you describe that structure, what geometry you assign to it, depends on your observational perspective, just like in relativity where simultaneity depends on your reference frame. It's observer-dependent but not arbitrary. So is space real? Yes and no. It's real in the sense that it has measurable properties and predictable behavior. But it's not fundamental in the sense of being part of the basic furniture of reality. It emerges from quantum information the way temperature emerges from molecular motion. And here's why this matters. If we keep thinking of space as fundamental, we'll never understand quantum gravity. We'll never resolve the paradoxes of black holes. We'll never understand what the universe was like before the Big Bang, because we'll be asking questions in a language that doesn't apply at that level. It's like trying to understand molecular chemistry by talking about temperature and pressure. Those are useful concepts for gases, but they don't help you understand chemical bonds. You need to talk about electrons and quantum mechanics. Similarly, we need to talk about quantum information and entanglement, not space and geometry, to understand the deepest levels of reality. I've been working on this problem for decades and I still find it disorienting. I walk through a room and I see space. I see distances. I see 3 dimensions. It all seems so solid and real. And then I remember that it's an approximation, a high-level description of something more abstract. The room I'm in emerges from correlations between quantum fields. The distance from here to the wall is a measure of how entangled the field states are at different locations. It's real for practical purposes, but not fundamental. And at smaller scales or higher energies, that description would break down completely. Does this mean we're living in a simulation? No. Simulations are programs running on computers, existing in some other space. I'm not saying that. I'm saying space itself is information theoretic. The universe is computing itself in a sense, but there's no external computer. The quantum state is all there is, and space is one way of describing aspects of that state. This is probably the hardest idea in modern physics, harder than curved space-time, harder than quantum superposition, because it asks you to let go of something so basic that you never questioned it, the existence of space, the thing you're in right now. But if physics has taught us anything, it's that common sense is a terrible guide to fundamental reality. Common sense says the Earth is flat and stationary. Wrong. Common sense says time flows at the same rate everywhere. Wrong. Common sense says objects have definite properties independent of observation. Wrong. And common sense says space is real and fundamental. Also wrong. Every time we've challenged common sense and followed the mathematics, we've discovered something deeper and stranger. And I think this is the next step, understanding that space is emergent, that geometry comes from information, that the stage where physics happens is itself part of the physics. We're not there yet. We don't have the final theory. But the clues all point in the same direction. Black hole thermodynamics, holography, entanglement, ADS CFT. They all suggest that space is not what it seems, that if you could look at reality without the filter of human perception, you wouldn't see 3-dimensional space. You'd see something else entirely, an abstract quantum structure with no geometry at all. And from that structure, through the patterns of correlation and entanglement, space emerges, not all at once, not perfectly, but well enough that at our scale, with our observations, it looks real. It looks like the fundamental thing. But it's not. It's a map, a description,